Hi class, welcome to Unit 4, Lesson 4. We'll be looking at light, wave, or particle. Learning goal today, students will demonstrate understanding of Newton's particle theory and Huygens wave theory. Success criteria, if you know you've achieved the goals if I can describe in detail Newton's particle theory and Huygens wave theory, identify the difference between wave and particle, and apply learning to daily life problems. So, a brief history of light. In 1000 AD, it was proposed that light consisted of tiny particles. Newton used this particle model to explain reflection and refraction. And then Huygens came along in 1678 and explained many properties of light by proposing light was actually a wave. So we had Newton and his particle theory and Huygens and his wave. Then we had Young in 1801, who showed strong support for wave theory by showing interference. And then we saw Maxwell in 1865, who showed electromagnetic waves travel at the speed of light. Then Max Planck came along and showed electromagnetic radiation is quantized, which implies and shows support for the particle theory. And he explained the light spectrum emitted by hot objects in his work. And then Einstein came along and he said that particle was part of the nature of life, and that in parts of its aspects it also behaved as a wave. So he said it wasn't exactly wave or particle, but both really, and it became the basis for the modern particle wave duality theory for light. So by the 17th century, contradictory views of the nature of light placed scientists into two opposing camps. One was Newton's, who was the principal advocate for it being a particle, or corpuscular theory. So Newton was behind that one mainly. One of the principal advocates of the competing wave theory was the Dutch Christian Huygens, who was also a mathematician, physicist, and astronomer. The debate continued for more than 100 years. By the late 19th century, there appeared to be overwhelming evidence that the nature of light could be better explained using the wave model. So Newton's corpuscular theory in 1704, he proposed that light consists of a stream of small particles because it travels in straight lines at great speeds and is reflected from mirrors in a predictable way. He observed that the reflection of light from a mirror resembles the rebound of a steel ball from a steel plate. And since he made such progress in motion and forces, it kind of makes sense why he was an advocate for the particle theory and observing things like this predictable motion and particles. So when we look at particles versus waves, we can say that particles have position and they have changes in position. So you can have x0, x1, you can have delta x. Particles have mass, which affects things like momentum, P equals mv, and it affects their acceleration, their effect in net forces applied to them. And so particles have some of those qualities. Whereas waves, we've seen they have wavelengths of lambda. They have amplitudes and frequency, number of cycles per second. And they have crests and troughs and are subject to constructive and destructive and constructive interference. Not so much how like projectile motion or anything like that, like a particle might look into, but it's concerned with its different ways of movement through interference. So when you look at and compare the two, particle is localized in space and has discrete physical properties such as mass. A wave is inherently spread out over many wavelengths in space and could have amplitudes in a continuous range. And like I was saying before, a major difference is waves superpose and pass through each other through different types of interference, constructive and destructive, while particles collide and bounce off each other. So instead of combining constructively or changing destructively, particles are subject to more Newtonian physics and stuff like collisions and projectile motion and those sorts of types of motion of physics. So Christian Huygens was alive 1629 to 1695. He's best known for his contributions to the fields of optics and dynamics. And he's the one who deduced the laws of reflection and refraction. And we saw how important those were with many examples from mediums and how important it was to observe. And he also explained double refraction, which we saw a few lessons ago. So his principle said that every point on a wave front can be considered as a point source of tiny secondary wavelets that spread out in front of the wave at the same speed as the wave itself. The surface envelope, tangent to all these wavelets, constitutes the new wavefront. He assumed that light is a form of wave motion rather than a stream of particles. So they came together and made this envelope which constituted the new wavefront. And his principle is a geometric construction for determining the position of a new wave at some point based on the knowledge of the wave up front that preceded it. So what did this wavelet and new wavefront look like? Well, here's a nice diagram of this. So at t equals 0, the wavefront is indicated by this line. And we have these points. And these points are the ones that are going to generate the new waves. So these are the sources, kind of like we saw a couple lessons ago with, they're like S1 and S2. They're creating waves, and this is creating a wave, this is creating a wave, and they're constructing against each other, and they end up looking like this one produces this one, and then this point would produce this one, and here time with a little bit of time it would be a little bit forward. And so after moving this distance of c delta t, these are all moving this distance all the way from A to all the way to B. Once it gets to this new spot here, we can form a new line, B prime, which is tangent to all the wavelengths. So at each point, just touches that one point, and we have a new straight parallel to the previous one wavefront. And so this is what Huygens was saying, that the wavefront would produce new wavelets that would move forward and create the new wavefront. And so he knew that spherical waves he had to also prove, and so we can see that his concept was similar. He would have points from the initial wavefront that would propel each source would give these wavelets, and they would also move c delta t radially outward. And when they're all in phase, they make this new wavefront that's, again, tangent to all these points. It's just not straight anymore, but it's a nice circle, but it's still tangent to the vertexes. And so he expanded, he made sure to prove the spherical wave as well, because everyone observed straight waves, but also waves coming out in a circular pattern. So Huygens' theory had a lot of promise and explained a lot of properties of light, a lot that we've seen, including reflection and refraction, the partial versions, diffraction, and a lot of the big concepts we've covered. The wave theory was more valid at that time than Newton's corpuscular theory, but because of Newton's reputation and all the work he had done at the time, he was kind of overruled a little bit, and so Newton's theory went forward instead for 100 years, until such time Thomas Young came along and he provided some nice new evidence in 1807 to help bring Huygens' theory back on top. Newton's particle theory provided a satisfactory explanation for some of the properties of light: rectilinear propagation, reflection, refraction, and dispersion. But it wasn't strong in explaining some of the things Huygens could, involving partial reflection, partial refraction, and diffraction. As we saw, Huygens' wave theory was the idea of having a certain wavefront, and it would have many sources on the wavefront, which would produce new little wavelets, which would move forward c delta t. And then at some point, you get a nice new straight wavefront that constitutes the new wave, this new tangent line that's tangent to each one of these little wavelets. And that was what Huygens was trying to argue. And it explained many of the properties of light, including reflection, refraction, especially partial reflection and partial refraction, and diffraction, which Newton couldn't explain very strongly. And so what do all of you think? Is light a particle? Is light a wave? Could it possibly be both of them in some regard? How would they work? Give it a thought. And that's the end of the lesson for today.